We have like radicals if the index is the same and the radicand, the expression underneath the radical, is exactly the same. So let's look at this first example. It says, what is the simplified form of each expression? We have 3 root 7 plus 11 root 7. If you ask yourself, okay, if I have 3 of these things and someone gives me 11 more of these things, how many of them do I have? Well, I have 14 things. The things just happen to be root 7s. So I can see that I'm really just adding the coefficients. It's 14 root 7 for the final answer. The identity of the radical is unchanged. It's a square root of 7. I just have more of them. In the next problem, I check. My radicals are like radicals. They're both cubed roots, and they're both have a radicand of 5. So I have 3 of these things, and I add 8 more of them. So that gives me a total of 11 cubed roots of 5. In the next problem, I check again. I see that I have an index of 4 and then an index of 3. So it doesn't matter that they both have the same radicand of 5. They're different roots. The first one is what number times itself 4 times gives me 5. The second one is what times itself 3 times gives me 5. Those wouldn't be the same number. So that is the simplified form of that expression. I can't do anything else to it. Sometimes it looks at first like they're not going to be like radicals, but there's some work that I can do that could make them like radicals. So when I'm initially given this problem of the square root of 27 plus the square root of 75, I'm like, well, they're both square roots, but they have different radicands. I can't do that. But then I'm like, wait a minute. We've done the square root of 27 before. That's the square root of 9 times the square root of 3, or 3 root 3. I wonder if I can simplify radical of 75 the same way. I'm like, hey, yeah, 75 is 25 divided by 3. I picked 25 because it's a perfect square. Well, that means that's 5 root 3. And now all of a sudden I have like radicals. Not only are they both square roots, but they both have a radicand of 3. So 3 root 3's plus 5 more root 3's gives me 8 root 3's. And sure enough, I can simplify this expression even though they didn't appear to be like radicals at the beginning. Next, we're multiplying with radicals. That's a little different than adding. When I'm multiplying with radicals, I don't actually need like radicals. All I need is the same index. And if I have the same index, I'm able to multiply underneath. We've actually been using this rule in lesson 2 when we were simplifying radicals by breaking them up. So here's the idea. I've got the square root of 5 times the square root of 6, and neither 5 nor 6 is a perfect square, nor are they divisible by perfect squares. So I'm just going to multiply under the radical and get the square root of 30. Next, I have the square root of 9 times the square root of 16, and before I multiply, I always want to see, could I maybe simplify that first? And I notice that 9 is a perfect square. In fact, it equals 3. And 16 is a perfect square. In fact, its root is 4. So all I really need to do is 3 times 4, which is 12. Now, let's say I wasn't paying attention. I might have done the square root of 9 times 16, which is, let's see, 90 and 54 would be 144. And lo and behold, the square root of 144 is 12. So I could have done this problem inefficiently by not realizing that I could simplify first, but I should still be able to get the correct answer. When I have something like the last problem, I need to realize that this is a distribution problem. So first, I'm doing root 3 times 3, which will be 3 times root 3. And then I'm subtracting the square root of 5 times the square root of 3. Well, neither 5 nor 3 can be simplified this way, so all I can do is multiply them. I'm going to have 3 root 3 minus the square root of 15. Although those are both square roots, they don't have like radicands, so I can't simplify any further than that.